Okay, so today we're gonna be talking about the photoelectric effect. And right here, as you can see behind me, I have the actual diagram of the experiment itself. And like any electrical circuits, we have the wires, we have the power source, we have the rheostat, the ammeter and voltmeter, just to put them there, and two metal rods act as an anode and a cathode. Now, due to the positioning of our power source right here, the positive charge goes to the anode and the negative charge goes to the cathode. Now, what happens in this experiment? Well, electromagnetic radiation, also known as photons, also known as light, is striking onto the surface of the cathode right here. Now, what that does is that photoelectrons are then emitted from the cathode to the anode surface, and as this goes on, there produces a flow called a photocurrent, and since it is directly proportional, so the higher the potential difference between the cathode and the anode, the more photoelectrons will go to the anode and the higher the photocurrent. And if there is less potential difference between the cathode and the anode, the less the photocurrent, meaning less less photoelectrons reaching the anode. And what happens when there's exactly no potential difference? Then there would be no electrons reaching the anode, meaning that there's no photocurrent. Okay, now let's start things all over again. We put the photoelectrons back on the cathode and keep the anode all by himself. Okay, so what happens if we change the terminal of the power source? Ta-da! Now what happens when this? So the anode is now negative charge and the cathode is now, the anode is negative charge and the cathode is now positive charge, as you can see here. Now what that does is that it decreases the positive charge of the anode and it increases the negative charge, so meaning that just less photoelectrons will actually reach the anode. Now maybe there will be just a few, but not a bunch of them. Now since there's like no photoelectrons reaching the anode that much, there's really not much of a flow, then there's basically no photocurrent. That's no current. And what we call the electric potential at this point is actually the stopping potential, which is the minimum reversed voltage where there is no photoelectrons reaching the anode. And it is also something that we apply to stop the photoelectrons that has a maximum kinetic energy, also known as Kmax, means that the fastest electron. So we also do this to stop the fastest electron. Now you might be wondering, since this is an experiment, there must be something we can manipulate to change the result somehow. Something that we can mess around with. And basically you're right. What about instead of the power source, we could actually mess up with the metal rod or the cathode right here. And if I move to my left side, I actually put up something called this equation right here, which is something to do with the metal itself. Now we know the full story as how the electrons are emitted, but when light energy strikes onto the metal surface, the light energy, a fraction of it is actually being used to emit the electrons. So the work being done there is actually called a work function, as what we symbolize as W naught. So what is W naught? What is the work function? The work function is a minimum amount of energy required to emit electrons from the surface of the metal. As you can see the equation right here, we also have the equation that equals to the Planck constant multiplied with the, what seems here, F naught, what we call is the threshold frequency. And kind of similar to the work function itself, the threshold frequency is the minimum frequency that is required to emit the electrons in the first place. So these two kind of work in the same way. Yeah, so that's basically much it for today's video. Thank you so much for watching, and I guess I'll see you later.